Hello everyone, I'm Jae-Wan from Zhejiang University. I'm a second-year PhD student who focuses on the AI security. I'm here to present our work, Bounce Attack, a query-efficient design-based adversarial attack bouncing into the wild. In our paper, we mainly focus on the traditional classification model. The attacker will add human invisible perturbation to the benign sample to transform it into the adversarial sample. The adversarial sample will not change the human recognition of the original input, but will make the classifier to give an incorrect prediction. Before we start, we make following notations. We use XT to simplify the adversarial sample optimized in the TIS iteration. XT hat is the adversarial candidate sample in the TIS iteration, and X star is the benign sample, and the XA is the expected optimal adversarial sample. Following the same gradient estimation strategy as adopted in HSJA, bounce attack will start with an adversarial chosen sample from a random classes in the untargeted setting and a certain class in the targeted setting, and optimize the perturbation to reduce its size in an iterative manners. Bounce attack will first conduct the binary search to project the adversarial sample on the design boundary to acquire the adversarial sample in this iteration, and move the adversarial sample into the adversarial space along the bounce direction. With the number of the iteration increasing, the perturbation size converges to a small constant value and the attack ends. Our methods are composed of three components. The first one is a bounce search. The bounce search uses the bounce decomposition operation to decompose the estimated gradient along the orthogonal direction of the hyperline from the benign sample to the adversarial sample. This proof can be found in the theorem 1 in our paper. If we fix the step size, the projection of adversarial sample will move as far as possible from the benign sample on the design boundary. The bounce vectors produced in each sample point might be largely affected by the randomness of the unit vectors in the gradient estimation process. The momentum can smooth the search process to mitigate such a problem. The hyperparameter mu in the momentum controls the memory of historical search direction. When mu is small, the search direction will be largely affected by the newly generated bounce direction. When mu is large, the search direction will be greatly driven by the historical information of past iterations. The bounce direction can lead to a fast convergence of the adversarial sample on the design boundary, but it might lead to fluctuate back and forth across the optimal adversarial sample in the end as shown here. We will switch to smooth search to mitigate such a problem. We will adopt the gradient directly instead of decompose the gradient into the bounce direction. In the experimental setup, we attack the ResNet 50 and the DenseNet 121 models trained on CIFAR 10, CIFAR 100, and ImageNet datasets as our victim models, respectively. We conduct the experiment with several baseline methods, which also focus on the black box adversarial attack setting. Our method can be applied in every attack setting. Under either the L2 or L infinite constraint, Bunster tank is able to craft an adversarial sample with a limited number of model queries to obtain a small size perturbation in the attack process. Within 5,000 model queries, Bunster tank reduces the perturbation size by over 40% compared with other attack methods across all the experiments. Within 30,000 model queries, Bunster tank can still hold its first place and outperform others. Given the same threshold, Bunster tank can always achieve the best attack success rate. As the number of model queries increasing, the attack success rate of Bunster tank can always be more outstanding than other methods. Under different defense methods, Bunster tank can always acquire the best performance. We calculate the rate of the average attack success rate of other attack methods to that of ours and find that other attack methods can maximally reach 87% attack success rate compared with Bunster tank across all the experiments. To gain insight how Bunster tank succeeds in scenarios where existing attacks fail, we compare the attack process with HSJA and Bunster tank on the same random chosen sample. HSJA fails to generate an adversarial sample within 30,000 queries, but Bunster tank succeeds. However, if we switch the attack method from HSJA to Bunster tank at 10,000 number of model queries, the tank quickly converges to a distance smaller than the threshold, resulting in a successful adversarial sample. This demonstrates that, compared with the gradient estimation in the HSJA, the bounce direction used in Bunster tank indeed improves the query efficiency as well as the attack success rate. In the untargeted setting, Bunster tank can hide the adversarial perturbation into the Belay image within 1,000 model queries in the visual perspective. In the targeted setting, Bunster tank needs around 5,000 model queries to hold the target image into the benign image. With the attack going on, the generated sample look more and more similar to the benign sample. And we draw such conclusions. Bunster tank decomposes the estimated gradient for the design-based black box adversarial attack. It shows good performance under both L2 or L infinite constraints in both targeted and untargeted settings. We provide analysis of why bounce vectors can help to obtain a small perturbation distance. Extensive experiments are conducted to show that Bunster tank is outstanding in both query efficiency and attack success rate. Thank you.